So far we've talked about centripetal acceleration and a couple ways to calculate it. We have the basic centripetal acceleration equals v squared over r, and then we also said, well, centripetal acceleration can be calculated in terms of period for pi squared r over t squared, or in terms of frequency where centripetal acceleration is for pi squared r times the frequency squared. Okay, those three equations work, but what we really have to get into is why do things accelerate in a circle to begin with? Okay? Well, if you think about why does the moon revolve around the Earth? The moon's out here. There is a gravitational force of attraction towards the center of the Earth on the moon. So this force due to gravity is actually what causes the moon to accelerate towards Earth, and because it's got a tangential velocity going this way, it moves in a circle around Earth. Okay? So that one we'll get into later when we talk about universal gravitation. But what about when you spin something in a circle around your head or something? So let's say you've got, I don't know, like a 5-kilogram mass, which would be really heavy, and you're spinning it in a circle around your head. What's providing the force to keep that thing going? Well, it's the tension in the string. Okay? That tension causes the acceleration. And finally, what if we have somebody who's on a flat, horizontal level road and they have to turn a corner? So they end up going around this way. What's providing that force? That one's a little bit trickier to understand. This one, okay, gravity pulls on objects with mass. This one, the string is connected to the thing. Clearly, if the string breaks, then the little mass goes flying out that direction. But what keeps the car on the road? Well, if we look at a car sitting on the road, normally we think of two forces acting on it in the vertical direction, and those two forces are gravity down and the normal force up, and they balance each other as long as the road is horizontal. Okay? Well, when we start putting friction into the middle of this, then there could be a frictional force, and we tend to think of friction as slowing the car down. But when it's turning this corner, right, the car has inertia that wants to keep it going this way. There has to be a force in towards the center, and the reason that that force exists is because there is traction or friction between the tires and the road. So there's actually a frictional force that provides that. Now, we need to be able to identify the agent, but we also have to be able to figure out how much force that is. For that, we go back to Newton's second law, which just says net force equals mass times acceleration. Okay. When something's undergoing uniform circular motion, we know that its velocity is changing only in direction. What I mean is the speed isn't changing, the direction is changing. So that means there is no acceleration around the circle. It's not getting faster or slower in this direction, but it is accelerating in towards the circle. So when something's undergoing uniform circular motion, the only acceleration is centripetal acceleration. So the only force is the force that causes centripetal acceleration, and creatively we call that centripetal force. So in this case, in uniform circular motion, the net force is equal to the force that's causing it to seek the center, the centripetal force. So the net force is the centripetal force, and that's just mass times centripetal acceleration. So if we wanted to look at any of these problems, we could figure out how much force is in the string, or how much friction we need to turn this corner, or even how hard gravity pulls on the moon.